Welcome to the fourth lecture of the linear programming. We continue this session with the graphical methods. Here I have taken a new case of minimization. The objective function is minzad 20x1 plus 40x2. It is subjected to three constraints: 36x1 plus 6x2 is greater than or equals to 108, 3x1 plus 12x2 is greater than or equals to 36, and 20x1 plus 10x2 is greater than or equals to 100, subjected to non-negative condition x1 and x2 should be greater than or equals to 0. So the first step still remains the same. These inequalities are converted into the equalities. So I am rewriting the equation 36x1 plus 6x2 equals to 108, 3x1 plus 12x2 equals to 36, and 20x1 plus 10x2 equals to 100. Now I require to compute the intersection of these lines with the x-axis and y-axis. To compute the intercept of these lines with the x-axis, I require to take y component as a 0. So I am writing, if I am taking the y component as a 0, so what will be the case of this one? If I am taking x2 here as a 0, that is y component, it gives me a 36x1 equals to 108. So 108 divided by 36, so it gives me a 30. Likewise for this one, if I am taking the y component x2 equals to 0, corresponding to that the equation will be 3x1 equals to 36. It gives me x1 equals to 36 divided by 3, that is 12. So it is 12, 0. Similarly, if I am taking this x2 as a 0, x1 gives me as a 5. Likewise, to compute the intercept with the y-axis, I am taking x component as a 0. So if I am taking the x component here 0, so 36x1 will become 0. It gives me equation 6x2 equals to 108. So x2 equals to 108 divided by 6, and it gives me a result of 18. Likewise, here if I am taking this as a 0, so 12x2 equals to 36. So this is 3. And likewise, if I am taking this as a 0, x2 becomes a 10. So these are the intercept with the x-axis and y-axis. Now I need to take a graph. I must write the scales of x-axis and y-axis. The scale here I am writing as 1 centimeter equals to 2 units. On x-axis 1 centimeter equals to 2 units, and on y-axis again 1 centimeter equals to 2 units. So this is my x-axis, this is my x1 variable, this is my x2 variable. So this is 2, 4, 6, 8, 10, 12, 14, 16, 18. Likewise 2, 4, 6, 8, 10, 12, 14, 16 and 18. For the first line, intercept points are 30 and 018. So 30 is this one, this is 018. Connect these two dots. refer back to the original equation. For the first line, the inequalities are of greater than or equals to, so the arrows will be in upward direction. Arrows are in upward direction. Labeling is important. The equation of this line is 36x1 plus 6x2 is greater than or equals to 108. Second, for second the points are 12, 0 and 0, 3. 12, 0, 0, 3. Connect the dots, connect these points. Inequalities is again of greater than or equals to type, so yes, greater than or equals to type. Label the equation, label the line, that is 3x1 plus 12x2 equals to 36. Inequalities are of greater than, hence the arrows are shown in a upward direction. Third, for third it is 5, 0 and 0, 10. So 5, 0 is this one and 0, 10 is this one. The equation for the line is 20x1 plus 10x2 equals to 100, and inequalities are again of greater than type. So what is the bounded region in this case? For the first line, this is the constant equation that entire region should be greater than this. For second line, the entire region should be above this line, and for the third case, the entire region should be greater than this. So what is the common region for all these three lines? What is the intersection of these three lines? So that gives me this particular region, this. This is the entire feasible region. This is the entire common region for these three lines. So whenever a region is not forming, the common region is not forming a polygon, a closed structure, so this type of region is referred as a unbounded region. If the region is closed structure, a closed polygon of n sides, that region is referred as a bounded region. This one is unbounded as it is not entirely closed. It is moving infinite in a upward direction. Okay. So what is the function? The function is of minimization type. And what are the points I am getting here? See, this is the one point. This is the 10, 0 point. I am getting one here, a point. This is my another point. The value of this point is approximately 2, and here it is 5.8. B is 2 and 5.8. This is my third point of the common region, C point. The point has 4 and 2 coefficient, 4 and 2, and this is the last point, D. It has a 12, 0. So I have got 4 points. I have got 4 points A, B, C, D. As such, the case is of minimization type. As such, the case is of minimization type. I require to put back this 4 coordinates back into the objective function, and I have to see that which particular point gives me a minimum value. So I have got 4 points A, B, C, D. What are their values? A has 10, 0, B is 2, 5.8, C is 4, 2, and D is 12, 0. What is my objective function? It is min z 20x1 plus 40x2. So what is the value of ZA? So it gives me a 200. ZB, so 20 into 2, that is 40, plus 5.8 into 40. So that gives me a value of 272. What is a C? It is 4, 2. So 20 into 4, that is 80, plus 40 into 2, that is 80 again. So it is 160. Then D, it is 12 into 20, so it is 240. So among these 4 coordinates, 4 points, which are identified from the graphical representation, this particular point C coordinate, it gives me the minimum value 160. Objective function is again of minimization type. It satisfies the best this equation. Hence, the value of x1 as a 4 and the value of x2 as a 2 should be selected, and corresponding the minimum value of the function is 160. Another numerical. Solve the following LPP using graphical method. Objective function is of maximization type, 100x plus 125y. It is subjected to two constant equation, 4x plus 6y is less than or equals to 24 and 4x plus 2y is less than equals to 16. So the first step is that these inequalities are converted into the equalities and we form a equation of line. So first line is 4x plus 6y equals to 24. Second line is 4x plus 2y equals to 16. If I try to compute the x-intercept, means y component equals to 0. So in that case, this will become 0. So x will become 6. Again over here, y will become 0, 4x equals to 16. So x equals to 40. Likewise, y-intercept, taking x component equals to 0. So this gives me a 0, 4 and over here 0, 8. Now we require to represent this line in a graph. So x-axis, y-axis, scale I am taking here on x-axis 1 centimeter equals to 1 unit, and on the y again 1 centimeter equals to 1 unit. The scale I have taken. So 1, 2, 3, 4, 5, 6. On the y-axis it is up to 8. 1, 2, 3, 4, 5, 6, 7 and 8. What are the points for the first line? 6, 0 and 0, 4. So this is 6, 0. This is 0, 4. I have connected the points, coordinates. Inequality here is of less than or equals to, means arrows are in a downward direction. The equation of this line is 4x plus 6y is equals to 24. For the second line, what are the coordinates? 4, 0 and 0, 8. 4, 0, 0, 8. connecting these two dots. Again, inequalities is of less than or equals to type, hence arrows are in downward direction. This line is 4x plus 2y equals to 16. The feasible region that satisfy the constraint 1 is this particular triangle portion, and the feasible region that satisfy my constraint 2 is this particular triangle. The common region between this intersection of these two is this one. Yes. So how many points I am getting here? A point, that is 4 0. This is my B point, that is 3 2. C point, that is 4 0, and D point I am getting, that is 0 0. So I write back these points, that A I got that as a 4 0, B 3 2, C I got as 4 0 again, and D is 0 0. So objective function I am writing, that is maximization of z 100x plus 125y. If I put the value of x and y in this equation, the ZA that I got here is 400, ZB that I am getting here is 300 plus 125 into 2, that is 250, so it is 550. ZC again is 400 and ZD is 0. The objective function here is of max z, and corresponding to this feasible solutions, the maximum value I am getting for this coordinate 3 2, means the x should be selected in a 3 units, y should be selected in a 2 units, and the maximum profit is 550. Moving forward with the graphical method, I have taken here the special case of graphical method. Instructions are given that use the graphical method to solve the following linear programming problem. Objective function is of maximization type max z 6x1 plus 4x2, which is subjected to constraints of 3x1 plus 2x2 equals to is less than or equals to 12, and x1 is greater than or equals to 3. Subjected to constraint equation x1 and x2 should be greater than 0. So I am redefining the equations with the inequalities are replaced with the equal to signs. So 3x1 plus 2x2 equals to 12, and x1 here equals to 3. So x intercept taking y component as a 0. So if I take x2 here as a 0, it gives me 4 0 coordinate, and this is 3 0. Likewise, y intercept taking x component 0. So if I take the x1 component as a 0, x2 becomes 6, and here again it is a 3 0 point, it remains same. Now if I try to plot this two equations on a line using by taking a suitable scale, so scale here I write that on x-axis again as a 1 centimeter is 1 unit, and on y it is 1 centimeter equals to 1 unit again. So 1 2 3 4 5 and 6, this is my x1, this is my x2, So for the first line it is 40 and 06. So this is my 40, this is 06. Connect these lines. The inequality here is less than or equals to type, so less than or equals to means arrows in a downward direction. This is the feasible region. The equation of line, that is 3x1 plus 2x2 equals to 12. For the second one, it is x1 equals to 3, means 30, a line that is parallel to y-axis, 30. What is the inequality? Inequality are of greater than or equals to type, means greater than means above this region on the right hand side. The value of x1 must be greater than 3, it should not be less than 3. So the common feasible region, the feasible region that satisfy the constant equation 1 is this triangle. The region that satisfy constant equation 2 is this particular region above this line, and the common intercept region is this one, this small triangle. If I try to write the points for this line, so in that case it is a point, that is 3 and 1.5, b that is 4, 0, and c that is 3, 0. I've got 3 points. If I write back these 3 points here, so a that is 3, 1.5, b that is 4, 0, and c that is 3, 0. What is my maximization function? That max z equals to 6x1 plus 4x2. So the value of za is 6 into 3, that is 18, plus 4 into 1.5, that gives me 6, so total is 24. What is the value of zb? So it is 24 again, and c that is 18. So the objective function here is of maximization type, max z, and I am getting the two values. I am getting the same value for two coordinates, a and b. So what it indicate? It indicate that this particular condition, this particular case follows the multi-optimality conditions. What is the multi-optimality condition? That the multiple choices, multiple selection of the variables, decision variables, multiple values of your decision variables satisfies the maximum conditions. Means on this graph, if I take any particular value on this line, on this particular region, any combination of x and y, corresponding to that I will definitely get the maximum value z. So this case is referred as a multi-optimality condition, means multiple optimal answers I am getting, hence it is a special case. Moving forward with the another special case, solve the following linear programming problem using graphical method. The objective function here is of maximization type, max z equals to 3x plus 2y. It is subjected to two constant equation, 5x plus 4y greater than 20, 3x plus 2y less than or equals to 6, subjected to non-negativity condition that x and y should be greater than or equals to 0. So writing them in the form of equality, in the form of linear equation, 3x plus 2y equals to 6. Compute the x-intercept by taking the y component equals to 0. So what I am getting here, x intercept 4y equals to 0, for x equals to 20, it means x equals to 4, 0. For this one, y equals to 0, so x becomes 6 divided by 3, that is 2, 0. Likewise, y intercept, by taking x component 0. So if I take the x component here 0, 4y equals to 20, it gives me 0, 5, and here 2y equals to 6, y is 6 divided by 2, that is 3. So plot them on a graph. This is my x, this is my y. Scale, I take here x as 1 centimeter equals to 1 unit, and y same 1 centimeter equals to 1 unit. For the first line, coordinates are 4, 0 and 0, 5. Okay, now coordinates are 4, 0 and 0, 5. 4, 0 is this one, and this is the 0, 5. Connect these two coordinates. Inequality sign here is greater than or equals to, means the feasible region that satisfies this condition is above this line. This line represents 5x plus 4y equals to 20. The second, 3x plus 2y is less than equals to 6. For that, there are 2, 0 and 0, 3. So this is my 2, 0 and 0, 3. Connect these two dots. Constraint inequalities here is less than or equals to type, means the feasible region is below this. This line represents 3x plus 2y equals to 6. Now see, in this case, the feasible region for this line is this one, for 5x plus 4y equals to 20. This region satisfies this condition. The feasible region for 3x plus 2y is less than equals to 6 is this one. Now the common region between these two constraint equation is null, it is 0, it is nothing, because both the constraints are separated, they do not have any common region. So this type of solution, okay, this type of condition will not result in a feasible solution. So this is referred as a infeasible solution. This is a case of infeasible solution. As the common region is null in both the case, the intersect of this two, the common region of this two is 0. So hence a feasible solution that satisfy this maximization condition 3x plus 2y cannot be established. Why it has happened? Because many times the constraints, when they are formulated in a mathematical equation, so at that time the correct proportion is not taken into the consideration, and that will result in this type of inequalities, this type of 0 common region, and that will result in a infeasible solution. So this is the second case that we have in a special cases in graphical method.